Hello, this podcast is on physical measurements. In this podcast, we're going to cover units, scientific notation, significant figures, and unit conversions. First, let's start with units. All measurements must have units, and that's the biggest difference between numbers in math class, which are usually unitless, and numbers in science, where our numbers are almost always measurements, so they need to have units. We'll be using the System International units. These are the worldwide accepted units for scientific research. And I want to talk about base quantities and base SI units. These are things that can be measured directly. And there are 7 of them: length, mass, temperature, time, amount of substance, electric current, and luminous intensity. In mechanics, we're going to focus on the first 3, length, mass, and time. So while we're going to be studying lots of quantities with lots of different units, we have to remember that they all relate back to 3 things that we can measure directly: length, mass, and time. And you can see the symbols here, and most importantly, we need to remember that length is measured in meters, mass in kilograms, not grams, and time in seconds. Well, if those are the only base units, what about our other units? Well, the other units are called derived SI units, and they go with the derived quantities. And these quantities and units are calculated from the base quantities and units. Let's take a look at some derived quantities and their SI units. Now again, this is just a partial list. There are hundreds of derived quantities. These are the ones that we'll use most often in mechanics: displacement, velocity, acceleration, force, momentum, work, and torque. Note, we cannot measure these directly. Even if we're using an instrument that gives us a direct reading, these quantities are all arrived at by calculating the base, doing some calculation with the base quantities of length, time, and mass. For example, velocity is calculated by taking length divided by time. Acceleration, you take velocity divided by time. And force, you take acceleration times mass. And so on with these other 3. Now let's take a look at the units. So you'll notice with force, it's got a long unit. This is the unit for force in base units. It's kilogram meters per second squared, or kilograms times meters divided by seconds squared. We've given this the special name Newton. For work, you'll look at the units. It's kilogram meter squared per second squared. We've given that the special unit of joule. And torque is kilograms meters squared per second squared, and we've given it the special term Newton meter. So this is a brief summary on units. Remember, most of our numbers in science are measurements, so we need to have units with them, and in this class we'll be using the SI units. Let's move on to scientific notation. We use this when we have very large numbers or very small numbers, and the numbers are written in the form m times 10 to the nth power. Here, m is a number greater than or equal to 1, but less than 10, and n is an integer. It can either be positive or negative. So let's take a look at some examples. If we have 6.5 times 10 to the 4th meters, this in regular notation would be 65,000 meters. If we had 2.49 times 10 to the negative 3 meters, this would be in regular notation 0.00249 meters. Notice that if the integer for the exponent is positive, we're going to have in regular notation a number larger than 1. And if the exponent is negative, we're going to have a number that's smaller than 1. Now let's look at some reverse examples. If we had 210,400 kilograms, we would write that in scientific notation as 2.104 times 10 to the 5th kilograms. If we had a really small number, such as 0.0000502 seconds, we would write that as 5.02 times 10 to the negative fifth seconds. By the way, this number is 502 10 millionths of a second. Really small number. Now, a word about doing calculations with scientific notation. I strongly encourage you to use the notation function. It's the EE button on your calculator, and you'll find it as a second function above the comma on your TI calculators. So for instance, in this last example, 5.02 times 10 to the negative fifth seconds, you should enter this as 5.02. The second button, the EE button, the negative button, and 5. Your calculator will treat this as one number instead of a series of math operations. So this is fewer keystrokes than if you entered 5.02 times 10 to the exponent negative 5. And so fewer keystrokes, it's quicker, less likely to make errors. Let's move on to significant figures. It's also known as significant digits, and we deal with this in science class but not with math class, and here's why. All measurements have uncertainty, and remember, in science our numbers usually are measurements, so it doesn't matter how careful you are taking the measurement or how expensive or precise your measuring device is, there will always be uncertainty in the numbers. Sig figs represent that uncertainty. They contain certain digits, an estimated digit, and sometimes they include placeholders. So let's take a look at an example. Here with ruler A, we can see it's measuring centimeters, and we've got tick marks or divisions that are tenths of a centimeter, also known as millimeters, and we're measuring the length of a nail. Here we have ruler B, it's the same nail, but notice the divisions are only every centimeter. We don't have divisions to the tenth of a centimeter. So while this nail is the same length, we're not going to be able to get the same amount of certainty from both the rulers. So for example, when we're reading ruler A, we know for sure that this is 4.3, but we know that it went past the 0.3 and stopped short of the 0.4 division. And so we can estimate this, and people could say, oh, it's 4.37, 4.38, or 4.39, but we know it's somewhere in that range. Now let's look at ruler B. We know it's longer than 4 centimeters, but it's way shorter than 5 centimeters. So we can estimate between these two tick marks or divisions, and it could be 4.2, 4.3, or 4.4. We don't know for sure. So when we're writing with significant figures, we would go ahead for ruler A and we would write this as 4.38 centimeters, or if we wanted to write it in meters, we would write it as 0.0438 meters. On the other hand, for ruler B, we would write this as 4.3 centimeters or 0.043 meters. Notice we don't have any hundredths of a centimeter because we have no clue what it would be based on this ruler that only has divisions every centimeter. So if we take a look at this in terms of significant figures, this number 4.38 or 0.0438 meters is written to 3 significant figures. This number 4.3 or 0.043 is only written to 2 significant figures. Now let's break down these figures. In the case of ruler A, the 4 in the ones digit and the 3 in the tenths digit, they are certain. We know what they are, no doubt about it. When we go to ruler B, we are only certain about the 4 in the ones digit. Back to ruler A, the 8 in 4.38 or 0.0438, these 8s are estimated. They could be a 7, could be an 8, or could be a 9. Moving on to ruler B, the 3 in 4.3 or in 0.043, these 3s are estimated. Could be 0.2, could be 0.4, or it could be 0.3. And then lastly, let's talk about placeholders. The 0 here in the 0.0438, these two zeros are placeholders. They're neither estimated nor certain digits. And similarly, over here, the two zeros are placeholders, neither certain nor estimated. So we can see that the number written to 3 sig figs has more precision, more certainty, because we have 2 certain digits and 1 estimated digit. Whereas the number written for ruler B with 2 sig figs, we're not sure of this digit here. We have no clue what the digit is for the hundredths of centimeters or the 10,000ths of the meters. So it would make sense that if we're using ruler A, we should write the number with more significant digits because this is a more precise measuring device than ruler B. Okay, let's move on with just some rules. For scaled instruments like a ruler or other analog devices that have tick marks or divisions, they could be a spring scale, it could be a thermometer, but obviously not a digital thermometer. You would record the value to the smallest division, those would be your certain digits, plus you would estimate 1 additional digit. So you're always estimating between the divisions. If you're using a digital instrument that has a readout, the last digit on the readout is the estimated digit. The digits before that are certain. So we have to be able to interpret numbers as to which digits are significant because scientists and engineers are going to write their numbers using significant figure rules. So first of all non-zero digits are significant. For instance, in the number 1225.3, all 5 digits are significant. 0 digits sandwiched between non-zero digits are significant. So, for instance, 1002 has 4 significant figures. These 2 zeros sandwiched between the 1 and the 2 are significant. Similarly, 1.001 has 4 significant digits because these 2 zeros between the 1s are significant. Next, 0 digits sandwiched between a non-zero digit on the left and a decimal point on the right are significant. For example, 1200 with a decimal point after the last 0 has 4 significant figures. These 2 zeros are significant. Now, if this was just written as 1200 without the decimal point, only the 1 and 2 would be significant digits. The 2 zeros would be placeholders. 0 digits to the right of a non-zero digit and a decimal point are significant. So for instance, here we have 2 zeros that are to the right of the non-zero digits, and they're also to the right of the decimal point. So all of these digits, all 6 of them, including these 2 zeros, are significant, and this number has 6 significant figures. That means we know with certainty to the 10th digit, and we're estimating that the 100th digit is 0. 0 digits to the right of non-zero digits with no decimal point are not significant. So, for instance, 1210 has 3 significant figures. This 0 is a placeholder. The 1 in the thousands digit and the 2 in the hundredths digit are certain, and the 1 in the tens digit is estimated. Similarly, as I had covered before, the 1,200 without any decimal point has two significant figures. The double zeros here are placeholders. The 2 in the hundredths digit is estimated, and the 1 in the thousands digit is certain. Finally, zero digits with only non-zero digits on the right are not significant. For instance, 0.0113 has three significant figures. These two leading zeros are placeholders. The 1 in the hundredths and the 1 in the thousandths digits are certain, and the 3 in the 10,000ths digit is estimated. And here, doesn't matter how many zeros we lead with, all leading zeros are placeholders. Okay, we still have more to learn about significant figures. How do we deal with scientific notation? Well, sig figs only apply to the m number, not to the exponent. So for instance, 1.00 times 10 to the fourth has 3 sig figs because we're looking at the m number, which is the number that comes before the times sign. And 1.0 times 10 to the negative 3 has 2 sig figs because again, the m number, 1.0, has 2 sig figs. So the n number only adds placeholders to the zeros, which is why it's not significant. So the exponent, whether it's positive or negative, that exponent is only adding zeros, and they will always be placeholder zeros. Notice the zeros written in the m number are significant, but zeros that are created by the exponents are placeholders. Now let's talk about how we do math operations with significant figures, because here we have to remember the answer to an equation or math problem can be no more accurate than the least accurate measurement. So here are the rules for addition and subtraction. The smallest significant digit in the answer is the smallest significant digit that all the measurements in the calculation string have in common. Well, what do I mean by that? Well, let's take 4.30 meters plus 7.0276 meters. Now clearly, this number here is much more precise, has much more certainty. And when we put them into our calculator, we're going to get 11.3276 meters. But do we really know the answer to that level of certainty? No. Our answer is no more certain than our least certain measurement, the 4.30. So notice that the smallest digit both numbers have in common is the hundredths digit. So we can write our answer to the hundredths digit, 11.33 meters. Now let's look at multiplication and division. The answer can have no more sig figs than the number with the fewest sig figs in the calculation string. So in this example, we have 6,385 meters divided by 98 seconds. Our calculator is going to give us 65.15306,122 meters per second. The calculator would tell us, or this number would tell us, that we know the velocity to the 100 millionth of a second. Was that possible when we only know the meters to the ones digit and the seconds to the ones digit? No, these digits over here are meaningless. So we need to look at the smallest number of sig figs in our division problem. And 98 has 2 sig figs. So we can write, or should write, our answer as 65 meters per second. That gives us the appropriate certainty with which we know the numbers. We're certain of the 6 in the tens digit, and the 5 in the ones digit is estimated. Maybe it's a 4, maybe it's a 5, maybe it's a 6. Okay, moving on. There is an exception to significant figures, and that's exact numbers. Well, what are exact numbers? Well, they are counted numbers. For instance, if 5 bananas have a mass of 0.875 kilograms, this measurement of kilograms has 3 significant figures, but does the 5 only have 1 significant figure? No, there's 5 bananas. We counted them. There's not 4.9 bananas or 5.1 bananas. There's exactly 5 bananas. So if we were to find the average mass, we would take the 0.875 kilograms and divide it by the 5 bananas. Because the 5 is a counted quantity, it's exact. So our answer would have the same number of significant figures as our kilograms measurement. There's one more category of exact numbers, and those are defined relationships. So for example, if we wanted to convert 525 meters to kilometers, we would take 525 meters times the conversion factor 1 kilometer divided by 1,000 meters. Now, does that mean that there's only 1 sig fig in this number and 1 sig fig in this number? No. The relationship between meters and kilometers is defined. Exactly 1 kilometer is equal to exactly 1,000 meters. So this conversion factor is an exact number. So when we do the math, our answer, 0.525 kilometers, should be to the same sig figs as our starting quantity, 525 meters. So some other examples of defined relationships: if you were going to the gas pump and the price of a gallon of gas was $2.49.9, that would be an exact number because we're defining the price. We're not measuring the price, we're defining the price. Okay, let's talk about rounding, because we need to round, because we've already seen where the calculator is always or often going to give us way more digits than we should report. So we're going to need to reduce our calculator answer to proper sig figs. So to do this, we look at the digit to the right of the smallest significant digit, or in other words, we're looking to the right of the estimated digit. And we have to decide, are we going to round up this estimated digit, or are we going to leave the smallest digit as is? So the general saying is, if it's 4 or below, leave it go. If it's 5 or above, give it a shove. So let's look at an example or several examples here. If we had 3.06 and we wanted to round it to 2 significant figures, we would have to look at the digit in the hundredths. And it's a 6. Well, that's 5 or above, so we're going to give the tenths digit a shove up to 1, 3.1. If we look at a number here with more digits, 3.0499 meters, and again, we want to round it to 2 sig figs, so we're going to round it to the tenths. We look at the number in the hundredths, and it's a 4. Well, 4 or below, leave it go. So we're going to round this to 3.0. Here we have 99.6 kilometers. It's going to round to 1.0 times 10 to the second kilometers. Now you may ask, why did I write such a small number in scientific notation? Well, I had to do this to show the correct number of sig figs. Because notice this 99.6, I'm going to look at the tenths digit. It's above 5, so I'm going to round this to 100. But if I write the 100 without a decimal point, just as 100, the zeros are placeholders, and that's going to be 1 sig fig. If I write it with a decimal point, 100 decimal point, then that's going to have 3 sig figs. It's going to make both zeros significant. And if I write it with the decimal point after the first 0, 10.0, well, that's not even 100. That's 10. So the only way I can write 100 to 2 significant figures is using scientific notation. And finally, if we look at 2,549 grams, and we want to round that to 2 sig figs, we would look at the tens digit. It's a 4, so that's less than 5, and we're going to leave the the hundredths digit alone, and this rounds to 2,500 grams. Let's take a look at another useful tool, unit conversions, and we're going to use the factor conversion method. Now, it's important to be able to convert units because often we may measure units in grams or centimeters or kilometers, but we need to convert them to the SI units, kilograms and meters, or we might be given time in hours and we need to convert it to seconds. So here's the process for the factor conversion method. We want to write an equality equation. So for instance, if we were going to be converting between kilometers and meters, the equality equation is 1 kilometer equals 1,000 meters. Next, we need to create two conversion factors from this equality statement. The first one is 1,000 meters divided by 1 kilometer, and then the second one, we just flip the numerator and denominator, and we get 1 kilometer over 1,000 meters. Next, we need to multiply the original measurement by the conversion factor that cancels out the original unit and leaves the desired unit. For example, if we wanted to convert 454.3 meters to kilometers, our original measurement is 454.3 meters, we need to multiply it by a conversion factor that will cancel out the meters. Well, if I have meters in the numerator of the original number, then my conversion factor has to have meters in the denominator. So I'm picking the conversion factor 1 kilometer over 1,000 meters. In step 4, we need to perform the calculation and cancel out the units that appear on the top and the bottom. So in this case, we have meters in the numerator and meters in the denominator, so they cancel out, and the only unit left is kilometers, and that's what we wanted to do, convert our original measurement in meters to a measurement in kilometers. Now, one note here, in this example, we were able to just use one conversion factor. Sometimes you may be doing calculations that require you to do 2 or 3 conversion factors. For instance, if you were changing days to seconds, you would have to use one conversion factor that converted days to hours, then you'd use another conversion factor that changed the hours to seconds. So again, you use the same process, but you may wind up with multiple conversion factors in order to get the final answer in the units you want. This ends our podcast on physical measurements, a very important part of doing science, especially in experiments and when it comes to problem solving. So you've learned about units, the SI units, significant figures, and unit conversions. I hope you found this podcast helpful.